everyone. In this video, we will talk about conditional expectations, which are an incredibly useful tool for modeling practice. So let's get started. These conditional expectations can be incredibly useful for us for finding expectations when we have what's called a conditional distribution, or a hierarchical model. Now, let's start by just providing the result, and then we'll see some examples of where this can really be beneficial for us. So if y1 and y2 are any two random variables, then we say that the conditional expectation of y1, or a function of y1, given y2 is equal to y2, can be found by taking simply that expectation over the conditional distribution. So we can either integrate using the conditional distribution, or we can sum using the conditional distribution. There are some shortcuts to finding this that can be really useful. Let's first work with this conditional distribution. So we have a soft drink machine with a random amount y2 of soda syrup and supply at the beginning of a given day. We're going to dispense a random amount y1 during the day with measurements in gallons. It's not resupplied during the day, so we know that y1 is less than y2. So there's some conditioning in this distribution. So let's find the conditional amount expectation of the amount of sales, given that y2 is equal to 1.5. So in a previous video, we actually found the marginal distribution and then the conditional distribution. So here's our conditional distribution. F of y1 given y2 is 1 over y2 for 0 less than y1 less than y2. In other words, our conditional distribution is a uniform distribution on 0 to y2. So our expected value of this conditional distribution is y1 times 1 over 1/2 dy1 integrated from 0 to 1/2 because we're conditioning on the fact that y2 is 1.5. So we then get 0.75 for our conditional expectation. Awesome. Let's say that we don't necessarily have that conditional distribution, or that conditional distribution takes on a different form. Think about it like this. In general, this conditional expectation y1 given y2 is actually a function of the observed value y2. We have to know what value of y2 we're observing in order to calculate that observed value, or that conditional expectation. However, we can also think of this conditional expectation as a function of a random variable. So certainly we could find this conditional expectation in terms of the condition, in terms of y2. If we do that, then we get kind of a neat result. So let's let y1 and y2 be random variables. Then it turns out that the expected value of y1 is the expected value of the expected value of y1 given y2. So if we take that expected, or that conditional expected value, find an expectation over it again, we get an unconditional expected value. When might you need to use something like this? Well, let's think about an example. We have a quality control plan for an assembly line that will involve us sampling n equals 10 finished items per day. Out of those 10 finished items, we'll figure out how many are defective. So we'll sample a small number off the manufacturing process. Now, if P denotes the probability of observing a defective, we can probably assume that Y follows a binomial distribution, assuming that we're sampling items off the line independently, that is. Now, let's say that the probability of defective parts changes from day to day. Some days the process might be running very smoothly, P might be near 0. Some days there might be a lot of hiccups in the process, P might be larger, say near 1/4. Let's find the expected value of the number of defectives, assuming that this P is allowed to change. So this is an example of one of those hierarchical models. There are levels. There's a hierarchy to our random variables. So the number of defectives that we pull off the assembly line, y, is actually a conditional random variable. This depends on P. Y given P, or y conditional on P, is binomial with n equals 10 and P being an unknown parameter. P itself has its own probability distribution. P follows a uniform distribution from 0 to 0.25. So if we want to find the expected number of defectives y unconditionally, we can do that by finding the expected value of the conditional expected value. So let's start with the conditional expected value. Y given P follows a binomial with parameters n p, so n times p is the expected value of that binomial. So our expected value of y is the expected value of np, or n times the expected value of p. So n times the uniform expected value, so 10 times 0.25 minus 0 over 2, our expected number of defectives is 1.25. Now, we also have a similar result for the variance. So let y1 and y2 be random variables. It turns out that the unconditional variance, so the variance of y1, is the expected value of the conditional variance plus the variance of the conditional expectation. So kind of cool, kind of wacky result. Let's find the variance of y with this. So to find the variance, we're going to take the expected value of the conditional variance plus the variance of the conditional expectation. So the variance of a binomial is n times p times 1 minus p. So we have the expected value of np 1 minus p plus the variance of np. We've got a little bit of algebra to work through. We get something that looks like this for our variance, plugging in n at the very end so we can kind of follow how this all works generally. We get an unconditional variance on y of 1.5625. Again, just a lot of algebra to work through this expected value and this variance. One thing I do want to point out here, notice that going from line 4 to line 5, rather than finding the expected value of p squared, what we have done is written this expected value of p squared in terms of rearranging the computational variance form. So that's really the only trick that we've needed to use here. Let's take a look at another example of one of these models. Max will harvest T tomatoes from his garden on a given day, where T follows a Poisson distribution, lambda. Each tomato will be checked for defects. The chance that a tomato has a defect is P. We'll assume that having defects is independent from tomato to tomato. Let's find the expected value and variance of the number of defective tomatoes. So tomatoes with a bite taken out of them, for example. We'll assume that P, the probability of a defect, is fixed. So y given T is binomial. The number of tomatoes that we're harvesting is itself a random variable, a Poisson random variable. So we'll start with the expected value. The expected value of y is the expectation of the conditional expectation. It's the expected value of the expected value of y given t. Y given t is a binomial, so expected value is pt. When we express that in terms of lambda, we get p times lambda, so whatever that lambda turns out to be. For the variance, we take the variance of the conditional expectation plus the expectation of the conditional variance. So we get the variance of pt plus the expected value of p times 1 minus p times t. This becomes similar to the previous problem. We have a lot of algebra related here. Our random variable is t, so we can write that in terms of a Poisson. Here we go, we get the variance. Now in the next section, we will switch gears just a little bit from looking at bivariate distributions to looking at transformations. Given that we know how a variable y is distributed, how can we find the distribution of a function of y? I'll see y'all then.